Decompression. In this module, you will examine the problems related to gas absorption and its release from the tissues, look at problems concerning decompression, find out more about no-deco stop diving, and discover some interesting studies carried out by researchers about these phenomena. Studying decompression. The study of the effects of decompression is one of the most fascinating aspects of diving. Your most important dive companion, your dive computer, will help you and suggest what to do in various situations. However, it is important to know how the computer works and why different models give different times, and what parameters are considered and which are not in calculating decompression. In short, you should know what your computer is doing. Only when armed with this knowledge will you truly master the situation and know what to do, even before your computer tells you. Empirical and mathematical models. The term decompression science is not totally appropriate, as the study of decompression has little to do with science but is actually rather experimental. It would be truer to say decompression trials. Study that is based only on experience and relies solely on trials is known as empiric. The decompression models still in use today are empiric, but have been tested in the field and are therefore very reliable. Empirical models are applied when there is no confirmed mathematical model available. For example, in some instances there are too many variables and it is impossible to consider them all. When dealing with very complex phenomena, the easiest thing to do is look at what happened in the past and presume that it will probably happen again if the situation is the same. The study of decompression was initially to try to translate real facts such as embolisms and sickness into a simple predictive mathematical model, so as to establish suitable safety procedures, later becoming tables and computer software. Later, work was done to improve this model, always comparing the changes with their practical applications in the field. Hard hat divers and caisson workers. Study of decompression theory began following problems noticed in other sectors, that of the caisson workers and the hard hat divers. It all began in England towards the end of the first half of the 19th century, when, due to the need to work underwater, the diving helmet was invented and was widely used. At the same time in France, they were developing a device for laying the foundations of bridges, the caisson. This system enabled the labourers to work on the riverbed and stay dry, or almost. A caisson is a large cylinder in cement with a vertical metallic tube down which the labourers can pass, and this tube leads to a small work chamber created at the end of the cylinder. Pressurized air is pumped into this chamber to prevent it flooding. All the interior is pressurized, so there is an equalizing chamber at the top of the tube where compression and decompression takes place, so it is possible to go in or out of the pressurized environment. As the caisson workers inside the work chamber dug the hole, the caisson slowly descended to the bottom. When it reached the correct depth, the caisson was filled with cement to fix it firmly to the bottom. But both caisson workers and hard hat divers suffered strange ailments and numerous incidents occurred that caused death or invalidity. The doctors of the time had no idea what was happening. During construction of the pillars for the Brooklyn Bridge, those affected were mocked because the strange contortions they made resembled the Grecian bend, an awkward but fashionable posture popular among the ladies of the time, hence the name the bends. First successes. It was only in 1857 that two French doctors, B. Paul and T.J.J. Vatel, clinically described the pathology, making the interesting affirmation, "You only pay when leaving." For the medical world, an embolism was completely anomalous. As long as the patient was compressed, he was completely well, and it was only when decompression occurred that the symptoms appeared. Then they disappeared as soon as the poor man was compressed again. Experimental observations in 1854 led Paul and Vatel to report on operative pressures, length of time at a particular pressure, speed of decompression, and the onset of symptoms. By discovering that recompression reduced the symptoms, the two scientists paved the way to solving the problems of the bends. More in-depth study on pressure variations was needed. It was the French physiologist Paul Bert who, in 1878, identified that nitrogen enters the tissues and blood in a solution, staying there as a dissolved gas as long as the pressure remains constant. He also established that if the pressure decreases quickly, nitrogen returns to its gaseous state before being transported through the body tissues and released outside the body. Baer proved that slow decompression was better, and he even pointed out the benefits of breathing normobaric oxygen. At that time, decompression was slow and continuous. In practice, it is as if we open a bottle of fizzy drink gradually so that the pressure is released slowly. Baer showed the maximum ascent rate to be about 1 meter a minute, 3 feet a minute, almost half that then in use by doctors in the British Navy. This reduction to the decompression rate greatly improved working conditions for most caisson workers and hard hat divers, and it also extended the operative depth limit to about 36 meters, 120 feet. But a mathematical model that simulated the absorption and elimination of nitrogen in the body tissues had to be created. In 1900, 3 German scholars, Heller, Mager and von Schrotter, elaborated a model that simulated what happens in a human body during compression and decompression. However, this model was extremely elementary, considering the enormous number of variables that can influence the absorption and elimination of gas in the body. The 3 scientists applied Dalton's law to air in pressure, calculating that the partial pressure of nitrogen in air is equal to 79%. However, they did not take into account the different tissues in the human body, but considered it as just one homogeneous mass. Saturation, undersaturation, oversaturation. Heller, Mager and von Schrotter used Henry's law to describe how nitrogen dissolves in the tissues, but in actual fact, the law is only valid for slightly soluble fluids. The maximum amount of gas that dissolves into a liquid is directly proportional to the pressure of the gas. Once this limit is reached, no more gas can dissolve into the liquid, even if you stay at that pressure for hours, days or months. This condition is known as saturation. If the pressure of the gas rises, the maximum limit of gaseous molecules dissolvable in the liquid increases because it is in a condition of undersaturation. So more gas molecules can pass into the solution until a new state of equilibrium is reached. If we decrease the pressure, the liquid will be in a state of oversaturation, so the gaseous molecules move from the liquid to the gas until a condition of equilibrium is reached. To measure the quantity of gas dissolved, researchers use the concept of tissue tension, a pressure referred to as PT. In practice, they indicate the pressure that corresponds to saturation of the same quantity of dissolved gas. In this way, it is easy to compare the different pressures: ambient pressure P, tissue tension PT. After a certain time, a tissue in contact with a gas at ambient pressure, which we will call P0, is in a condition of equilibrium, that is, in saturation. Consequently, the tissue tension has a value equal to that of the ambient pressure. Let's now immediately increase the ambient pressure, which we will call P1. As soon as the ambient pressure rises, there is a difference between this and the tissue tension, which has remained what it was previously. It is this difference, P1 minus PT, that pushes other gas molecules to pass into the tissue. When this happens, PT increases and the difference in pressure falls, P1 minus PT, lessening the force and reducing the speed at which the gas molecules pass into the tissue. Finally, after a certain interval of time, the tissue becomes saturated for the new pressure condition, P1, and the tissue tension PT now has the same value as P1. Returning the ambient pressure to the value of P0, there is once again a difference between the ambient pressure and the tissue tension, which is still equal to the value of P1. This time, the difference is PT minus P0. As this time, it is the tissue tension that has a higher value than the ambient pressure. This means that more gas molecules are dissolved in the tissue than that permitted by the condition of saturation. The tissue is said to be in a condition of oversaturation. This time, the difference PT minus P0 forces the gaseous molecules to leave the tissue and return to the gas. Also, in this case, the rate of elimination is initially fast and then gradually slows down. After a certain time, the tissue again reaches the equilibrium for the new condition of saturation for the ambient pressure P0. Its complete over-desaturation has taken place. The problem is that when gas molecules are eliminated quickly from the tissue, they tend to join together and form bubbles. For example, this is what happens with fizzy drinks. Opening the bottle cap causes a sudden fall in pressure, and the gas leaves the liquid quickly and forms lots of bubbles. Bubbles that form in the body can cause dangerous embolisms, and there are just two ways to prevent bubbles forming. Lengthen the time in which the pressure change occurs, or find out what the maximum acceptable pressure which does not cause a rush of bubbles is, and once that value has been reached, stabilize the ambient pressure for a certain length of time, after which another change in pressure can be made, and so on. This was the road that would be followed by JBS Haldane. The mathematical equation of half saturation times. The maths equation determined by Heller, Mager, and von Schrotter to describe the phenomenon is that of half saturation times, also known as half times. This law states that the period of half saturation T is the time tissue tension makes a change equal to half that needed to reach a condition of saturation. The law may be written like this, with the lowercase t representing elapsed time. If we begin from the initial moment, after an interval equal to t, we have a change of 50%. After 2 times t, we reach 75%, 50% of the first plus half the remaining 50%. After 3 times t, 87.5% is reached, 75% from before plus the remaining 25%, and so on, up to 6 times t, when about 98.5% is reached, which is rounded up to 100%. The equation determined by the 3 scientists therefore functions on the difference between the pressures, the half saturation time t, and the time of exposure. In the case of diving, P1 and P0 are established by the environment, so everything depends on the choice of the value of half saturation time t. This is an enormous simplification compared to the complex physiological reality. Heller, Mager and von Schrotter assumed that a man of medium build and with normal cardiac functions could be represented by a tissue with a half saturation time of 9.7 minutes. Haldane and the multi-compartment model. The birth of the submarine as a useful military tool created an enormous problem. How could the crew escape in case of an emergency underwater? This is why the British Royal Navy called in John Burton Scott Haldane, a physiologist and occupational medical doctor, to improve decompression procedures and produce more useful data for recovering trapped crew members. Haldane observed that the incidence of decompression sickness increased according to the exposure time up to a period of 5 hours, after which time there was no significant increase. Experiments using animals confirmed this observation. Therefore, if the human body had to be compared with a uniform tissue, its half saturation time must be such that it almost reaches saturation after 5 hours. Haldane estimated that this tissue had to have a half saturation time equal to 75 minutes, saturated to about 95% after 5 hours. However, on the other hand, even Heller, Mager and von Schrotter's tissue with a half saturation time equal to 9.7 minutes had had some success, even though it was limited to short exposure of up to 5 atmosphere. Haldane therefore established that the human body could not be represented by a single uniform tissue, but had to be considered as a unity of tissues. He created a mathematical model that simulated the human body with 5 tissues in parallel, with no gas exchange between them, with half saturation times equal to 5, 10, 20, 40 and 75 minutes. These tissues did not refer to any particular part of the body. They were simply mathematical expedients and were defined as compartments. Haldane's second important intuition was that the body could tolerate a condition of limited oversaturation with no problem. Seeing that dives of up to 10 meters, 33 feet, created no problems, Haldane conjectured that the halving of pressures was the maximum acceptable limit. Go! The US Navy tables. Thanks to the 5-compartment model and the identification of the critical value of oversaturation, Haldane created tables that revolutionized the way of decompressing. Instead of a slow and continuous decompression, the physiologist proposed decompression with stops, which for convenience were 10 feet apart from each other, the classic 3 meters, 10 feet. His model, elaborated in 1907 to 1908, is still valid today. Seeing the good results obtained, other countries also became interested in his theories and used his model. In 1915, French and Stilson created the Constructions and Repairs tables for the US Navy Bureau of Constructions and Repairs, and these tables were used successfully for 20 years. According to some US Navy researchers, the fast compartments could tolerate much higher values of oversaturation than the 2-to-1 ratio used by Haldane, and the test dives in 1937 had an incident rate of 1.1%, an acceptable figure for the Navy. To lower this percentage, work was done on the tables in 1951 by van der Auwe, who also took into consideration long working times. Studies and experiments established that the 5- and 10-minute compartments influenced the deeper decompression stops. In 1956, Dwyer, Desgrange and Workman extended the 75-minute compartment to 80 minutes and also included the 120-minute one to control the shallower decompression stops better. The fast compartments imposed unnecessary deep stops, but instead of cancelling these compartments, they decided to use higher maximum values of oversaturation for them, leaving the ratio unchanged for the 80-minute tissue and lowering it for the slower 120-minute one. They also established that these maximum values of oversaturation were valid for the return to the surface, but if a diver stopped before reaching the surface, it was possible to tolerate higher maximum values. All this was extremely complex, so Workman decided to establish the maximum value known as value M, which is the depth from which it is possible to ascend to the different depths for decompression. With the matrix of the M values, it was now much simpler to recalculate the tables. Using M values, you find that if you dive to less than 30 meters, 100 feet, the 5-minute compartment has no role in the dive, because even if you ascend to the surface, its level of oversaturation will always be less than the maximum acceptable value. So it will be other compartments that control the dive. It is therefore clear that the deeper the dive, the faster the compartment that controls it. The deeper the dive, the shorter the dive time, so you return directly to the surface. This is why the no-deco stop dives allow less time the deeper the dive. Tables for repetitive dives. There is a big difference if you use a computer or tables on your dive. Tables consider all dives as having a square profile, meaning that all the time is spent at the maximum depth. Instead, computers make mathematical calculations moment by moment following your actual dive profile. They consider the dive multi-level, or rather made at varying depths. So a computer usually permits longer dive times. This difference becomes even more important for repetitive dives. For Heller, Marker and von Schrotter's mathematical formula, you can consider that when an amount of time has passed that is equal to 6 times the half saturation time, a compartment has given up all its excess inert gas. So, the 5-minute compartment has given up all its excess nitrogen after half an hour. Instead, the 120-minute compartment needs 12 hours. Haldane's multi-compartment model considers that each compartment eliminates excess nitrogen during the surface interval at different speeds. This means that the tables for a repetitive dive are more than one. In fact, there are many, because they depend on the profile of the first dive. In order to have just one table, the US Navy decided to consider that during the surface interval, all the compartments released excess nitrogen at the rate of the slowest, therefore the 120-minute compartment. This is why the traditional US Navy tables considered any dive made within 12 hours, 6 times 120 minutes, from the end of the previous one as repetitive. After a first deep no-deco stop dive, the repetitive one was heavily penalized and could only be repeated at the same depth and for the same time as the previous one if 12 hours had passed. Instead, in the surface interval, dive computers can calculate the elimination of excess nitrogen in each compartment at its own particular speed. With the first deep no-deco stop dive, you only load the fast compartments significantly, but these compartments also release gas just as quickly. So after a short time on the surface, the computer considers that the fast compartments can be loaded again and allows you to repeat the dive to the same depth and for the same time as the previous one, sometimes even after just an hour from surfacing from the first. This advantage is only because dive computers make more precise and less simplified calculations. Boolman and gradient factors. The calculation of M values as depth in feet in salt water was a problem for those who wanted to calculate for dives made at altitude, therefore at heights that were not at sea level. So in the 1960s, Professor Boolman of the Institute of Hyperbaric Physiology of Zurich University used acceptable maximum values of oversaturation that no longer began with the absolute pressure of 1 atmosphere absolute at sea level, but from 0 atmosphere absolute, an absolute vacuum. A book with his mathematical models was published, and these models are still used today to program a lot of computer software. In 1995, Eric Baker proposed the method of gradient factors to reduce the maximum values of oversaturation in general. In practice, a setting of the gradient factors at 80% means that the maximum value of oversaturation used in the calculations is 80% of the acceptable value, thus reducing the bottom time allowed within the maximum no-deco stop times. In some computers, it is possible to set 2 gradient factors values, the gradient factors minimum and gradient factors maximum. What was said of the gradient factors in general is also valid for gradient factors maximum, while the setting of gradient factors minimum has little significance for no-deco stop dives. Limitations of the classical models. The objective of all the classic decompression models, Haldane's and those derived from them, is to prevent embolisms caused by bubble formation, but these mathematical models do not even consider the bubbles. According to the traditional mathematical models, when the no-deco limit is reached, you can return quickly to the surface with no problems. Instead, you know you have to ascend slowly. These contradictions show the limitations of traditional models. Thanks to research into bubble formation and growth, new decompression models have been created, and these will be examined in the next module. In the next module, you will find out what safety stops are, understand their importance, and establish the best line of conduct for diving at different depths. See you soon.